Hello everyone, my name is Abhiroop and I will be presenting my research paper on a machine learning consensus based lightweight blockchain architecture for Internet of Things. Firstly, I would like to thank the organizers and all the sponsors for providing me this opportunity to present my work in cybersecurity and privacy workshop of CompsNets 2022. The outline of the presentation is as follows. Firstly, I'll brief on the motivation behind our work. Next, I'll introduce the concepts of blockchain and IoT, discuss the security challenges in IoT environment and how blockchain can be used as a solution for those challenges. Next, I will talk about our proposed machine learning consensus based lightweight blockchain model for IoT, where I'll be describing our MCLB architecture and its overall workflow. Later, I will present the performance analysis of our proposed MCLB model, the experimental setup and the data generation methods, and finally, a performance matrix taken for our consideration. Finally, I'll conclude the presentation with the results and the future scope of our proposed MCLB model. Internet of Things forms a critical part of our day-to-day life as it is being employed in multiple applications. Due to its wide range of applications, IoT generates significantly large volumes of data whose security is of major concern. The erroneous and incorrect data generated from attacks on sensors or introduction of malicious sensor node may lead to unwanted results. Therefore, we examine the feasibility of blockchain at edge devices to enhance IoT security. So, what is blockchain? Blockchain is a digitized and decentralized public ledger that enables tracking of transactions digitally and share information across a distributed network. It was first revealed by Satoshi Nakamoto as a backend technology in Bitcoin to solve the problem of enabling trust in a distributed system. Blockchain uses the concepts of cryptography, hashing, and peer-to-peer networking. As you can see in the figure, it is a chain of blocks containing transactions linked to each other through their parent block hashes. Coming to Internet of Things, what is IoT? IoT represents a network of physical objects embedded with technology to sense and communicate attributes of interest. The data sensed from these interconnected objects helps to analyze environment, make smart decisions, and automate actuation processes. IoT is used in various industrial applications such as smart vehicles, smart homes, mobiles, online shopping, and many more due to its features like connectivity, scalability, and heterogeneity. As IoT involves billions of devices and large chunks of data, it requires a reliable and flexible layered architecture that consists of application layer, service management layer, network layer, and sensor layer. Even with this reliable layered architecture, IoT networks possess many security challenges and become target of cyber attacks as they deal with large-scale sensitive data. These attacks are categorized into physical level attacks, network level attacks, and software level attacks. Physical level attacks include node tampering, malicious node injection, and malicious code injection, which are addressed in our paper. Network level attacks include RFID spoofing and denial of service. Software level attacks include phishing and viruses. The current security mechanisms are constrained due to limited resources of IoT devices and centralized IoT architecture. Therefore, we examine the feasibility of blockchain for IoT. Blockchain is characterized by its distributed, transparent, and immutable nature that makes it unbreakable. Features of blockchain that make it attractive for IoT are anonymity that ensures privacy of the user, consensus that eliminates single point failures and ensures robustness, distributed architecture that ensures scalability, security. The cryptographic and hashing algorithms make the system impossible to alter or modify. Even though blockchain adoption in IoT has many advantages, still there exist few challenges such as complex proof of work consensus algorithm called as mining, which involves computation of a value nonce such that the hash value of block starts with given target number of initial zeros. As you can see in the figure, the time taken to calculate nonce increases exponentially with the number of target zeros, and such large delays are not acceptable in IoT environments. Second, the significant computational overhead for nonce computation. Third, the high communication overhead. The communication overhead created by blockchain protocol is not desirable for certain band-limited IoT devices. Therefore, in order to address these challenges, we propose our approach towards a machine learning based lightweight blockchain in IoT. In our model, we employ machine learning based consensus. The figure shows our MCLB model for IoT where all the edge devices in the network are incorporated with blockchain for data immutability, machine learning algorithm and aggregation module. The complex nonce computation is replaced by a machine learning based consensus approach which is robust, fast and enables detection of malfunctioning nodes. The machine learning algorithms extract trends and patterns for data classification and arrive at consensus. Use of same machine learning algorithm in all edge devices may compromise the predictions due to the implementation and accuracy of algorithm. So we make use of heterogeneous algorithms in our network model. Next, we introduced an aggregation module to reduce the data overhead. As IoT involves small chunks of data from large devices, the redundancy and repetition of this censored data may result in significant overhead. Therefore, we employ the aggregation module in each edge device to periodically aggregate raw data and create a set of metadata for every n samples of censored data. In our case, temperature, humidity, visible light and pressure parameters are aggregated over 60 samples to create a set of metadata such as mean temperature, max humidity and minimum pressure. The learning and classification by our machine learning classifier is carried out on this metadata. So, this is our proposed lightweight block structure where the block header contains block ID, Merkle hash, timestamp, node ID for sensor identification, edge device ID for edge device identification, and a parent block hash to link to its previous block. A single set of metadata readings in the block are fed to our classifier for classification. Hence, our edge device is incorporated with an aggregation module, machine learning algorithm, and a lightweight blockchain. Coming to the overall workflow of our MCLB model, at the edge device, when data arrives at EDA receiver module, it will check if data is from sensor or not. If the data is from sensor, the data is fed into aggregation module. The aggregation module generates metadata after collecting 60 samples of sensor data. A lightweight block is created with this metadata and is broadcast to the network for validation. Simultaneously, the block is also fed to its own classifier for validation and will wait for consensus from other EDs of the network. If the ED receiver module receives the data that is not sensor data, it will be checked for ED data. If the data is from ED and contains a block, then the block is fed to the machine learning classifier and the validation result is sent as a consensus message. When a consensus message arrives at the edge device receiver module, it will check whether the block has been validated, and if it is a valid block, then the edge device will add the block to the blockchain, or else the block is discarded. Coming to the experimental setup, in order to testify the efficacy of our MCLB model, we deployed an experimental testbed with 4 edge devices connected in mesh topology, where each edge device represents a separate sensing environment. Parallelly, a malicious nodes were introduced in each environment to trigger false actuation. Further, each ED is equipped with a specific machine learning algorithm such as support vector machine, naive space, decision tree, and nearest centroid. The hardware components in our network consist of iris modes with MTS 400 sensor board, and these modes are programmed in NESC running on TinyOS operating system. Later, we used desktop PCs as edge device running Linux Ubuntu 16.04 operating system. As part of dataset creation, we generated an IoT dataset consisting of environmental parameters such as humidity, light, temperature, and pressure read from 4 different environments. These datasets are used for training the machine learning classifier at edge devices. Data was generated periodically every 2 seconds over a week, and a sensor metadata is generated for every 6 samples of each environment. The figure shows the performance of our classifiers with SVM and nearest centroid having 100% accuracy, while Navy base and decision tree are having 99.9% and 99.85% accuracy in classifying the malicious data. Next, we'll see the performance metrics used for validating our MCLB model. First, It is average computational delay (ACD). It is the amount of time taken by an edge device for validating the metadata within a block. ACD is the ratio of sum of computational delays of all blocks to the total number of blocks validated. Second, average communication overhead (ACO). It is the amount of data in bytes that needs to be communicated for adding or discarding a block. ACO is the ratio of sum of lengths of packets involved in communication among edge devices to the total number of blocks. Finally, we have average block addition delay (ABD). It is the time difference between block creation and its addition to the blockchain. ABD is the ratio of sum of block delays to the total number of blocks added. The table shows the experimental results of our edge devices based on the performance metrics discussed. In order to evaluate the effectiveness of our MCLB model, we analyze the performance of MCLB by comparing with existing blockchain and centralized IoT models. It can be seen that the average computational delay (ACD) is least for MCLB as it does not involve nonce computation. Further, the MCLB has less block addition delay due to the removal of nonce validation. Moreover, in centralized IoT, there is no concept of block addition delay or there is no concept of communication overhead for blocks. Therefore, it is understood that our MCLB model outperforms the existing Bitcoin and centralized IoT models. In conclusion, IoT is a network of objects connected together and communicating over network through large chunks of data. Compromised nodes or malicious code injection attacks may result in unwanted actuation through falsified data. Therefore, we propose an MCLB model to improve this IoT security. The MCLB model showed better performance in terms of computational delay and block addition delay when compared to the existing blockchain models. Further, as a future work, we consider performing a security analysis of our MCLB model. Moreover, our model can be modified for incremental learning and data at edge devices. Thank you.